Hello everyone, welcome back to our channel. In this lecture, we will discuss the process of non-dimensionalization of the time-independent Schrödinger equation. We know from quantum mechanics, the time-independent Schrödinger equation is minus h bar square by 2m d2 psi dx2 plus v psi that is equals to e psi. All the symbols have their usual meaning. First, we consider some non-dimensional parameters, something like that is psi bar equals to psi by psi 0, x bar is x by some L is some characteristic length scale, and v bar is some v by v0 is some characteristic energy level, potential value rather, and e bar is e by e0 is the characteristics energy levels. Now we insert all these objects here in the Schrödinger equation, which is here psi is psi 0 psi bar and x is x bar L and v is v naught v bar and psi is psi bar psi 0 and e is e bar e0 and psi is psi bar psi 0. And after simplifying this, and we get this equation where d2 psi bar dx bar plus 2m L square by h bar square e naught e bar minus 2m L square by h bar square v naught v bar multiplied by psi bar equals to 0, and we make these two quantities 1, and after doing that we will get the differential equations, or rather TISE, time independent Schrödinger equation, in this form: d2 psi dx bar d2 psi bar dx bar square plus e bar minus v bar multiplied by psi bar equals to 0. This is a clean and sanitized form of time independent Schrödinger equation, and this is free from all other physical constants, and it is basically in this case these two constants are e naught is h bar square by 2m L square and v naught is h bar square by 2m L square. Now we come to the particular case, that is linear harmonic oscillator. We know for a one-dimensional linear harmonic oscillator, potential is Vx equals to half into k into x square, where k is a spring constant of the harmonic oscillator. Now if after putting this thing, the equation is something like that. Let us non-dimensionalize the equation similarly above, and after putting all these constant here, all these parameters here, and we get this equation, and after simplifying this we will get something like that, just like before. And here these are two constants, this object and this object, and make it 1, 2m e0 L square by h bar square and m L to the power 4 multiplied by k by h bar square, and that is equals to 0, and this object is 0 and this is 1. And if we put this thing 1, the equation becomes d2 psi bar dx bar square plus e bar minus x bar square psi bar equals to 0. This is our cleaned non-dimensionalized form of TISE for LHO, linear harmonic oscillator. This is my equation A, and these two constants are where E0 is h bar square by 2m L square and this object is 1, and from there we get L square is plus minus h bar by root over mk. This is the characteristic length scale, and if we put that L square into the energy equation, energy this E0, and we get E0 is h bar square by 2m root over only positive root of mk by h bar, and we will get this object. If we set k equals to 1 for numerical calculations, k equals to 1, m equals to 1 and h bar equals to 1, we get E0 is half. If we solve the equation A, this equation clean differential equation, or rather TISE, you will get, if you solve the equation A, you will get E bar basically, because our equation is in terms of E bar, but the actual energy eigenvalues would be E, that is E bar multiplied by E0. E0 is basically half. That means whatever you get whenever you solve the clean part is actually you have to multiply it by half, and then that will be the actual eigenvalue. From analytical consideration, we know energy eigenvalues are n plus half multiplied by h bar root of k by m, where n is 0, 1, 2 dot infinity. That means if h bar is 1 and k is 1 and m is 1, the eigenvalues are n plus half. Therefore, the energy spectrum is half, 3 half, 5 half, etc. But in our case, if we solve numerically that thing, the E bar will be half, D bar will be 1, 3, 5, etc. up to infinity. I hope you understand that, because E naught is half. This is your E and this is your E bar, and E bar relation is given by this equation. And for numerical solution, you always have to put your potential. This is your harmonic oscillator potential, that is half kx square. This object here is a axis here, and here x axis. You always, in order to solve TISC for a harmonic oscillator or any kind of potential, you need to confine the potential in the box, where psi goes to 0 at x goes to plus minus L. That is our artificial object, that is box. For a given choice of L, you can compute the finite number of eigenstates approximately. Higher eigenstates are much more spread out outside the dead wall region, thus the chosen boundary will be somewhat inaccurate. Then you have to increase the dead wall for getting the higher eigenstates, higher eigenvalues. In order to understand that, we concentrate on this figure. That is your potential well, that is your potential rather. This is your half kx square, and if you consider this red color, this is your supposed to be your dead wall, say here and here. As you reach the higher eigenfunction, that means if you consider on this object or this object, there are some part of the eigenfunction is spread out of the dead wall. That means as you reach higher eigenfunction, significant spreading is observed outside the dead wall. It means computation is inaccurate for higher eigenvalue. But for ground state, this wall is sufficient for making our wave function is 0. If you consider the ground state wave function, say psi 0 is 0 here and 0 here, that is somewhat accurate. And now we concentrate another problem, that is one-dimensional infinite potential well. We know our sanitized differential equation is something like that in terms of psi bar, x bar and E bar, etc. And here potential is 0 inside a one-dimensional infinite potential well, as you know from quantum mechanics. Here x equal to minus L, it is 0, and x equals to L is also 0, and outside it is that potential is 0 within that, and outside is infinity. This is called one-dimensional infinite potential well, or 1D box. Here we know E equals to E0 E bar, and E0 is h bar square by 2ml square E bar, and E bar by 2L square if m is 1. For analytical calculation, we know E is n square pi square h bar square divided by 2m 2L square. That means this object. If we take h bar was 1, m equals to 1, energy eigenvalues are n square pi square by 8L square. If make it L equals to 1 for numerical calculations, then E0 will be pi square by 8. That means if you calculate this equation, this sanitized equation, you will get the ground state energy 1.233700055. Depending on the accuracy, you will get this object, and first excited state is something like that, and second excited state is something like that. It is actually in a dimensionless form. You will get these energy levels. In the next lecture, we will definitely discuss the Python implementations of harmonic oscillator problem or 1D box problem using numerical technique. We also discuss the numerical, how to implement the numerical technique by using shooting method will be also discussed in the subsequent episodes. Thank you for watching. Please subscribe, like and share. Thank you once again.